Okay, so welcome to the second afternoon session of the conference. In this session, we will talk about Lorentzian structure of quantum gravity. We'll have three interesting talks. The first of them by Seth Asante from the University of Jena.
Yes.
So, the floor is yours.
Okay, thank you, Antonio. Okay, so thank you everyone for being here. Also, first of all, I want to thank the organizers for inviting me to this very nice conference. I was surprised by the invitation. It was a nice surprise, and I'm happy to be here. And also, it's nice to see familiar faces, of course, and I'm happy to meet new faces as well. I would also like to thank my collaborators. I mean, I've listed some of them here from whom I've learned a lot of physics. And actually, this talk I'm going to read now is collaboration with two of them here. Yeah, so thank you. And I chose to talk about causality violations in Lorentzian path integrals for discrete gravity. Rather than giving you a whole overview of Lorentzian quantum gravity, I chose this specific one. It's sort of an example, just so that I give you a feel of how this works. So bear with me. Okay, so I'll just start with motivation. So quantum gravitational path integrals has become very common. Many quantum gravity approaches are formulated on this. And you can actually see the difference, the different quantum gravity approaches as in the way they choose their, for example, the geometry they defined, and also the action associated to this kind of geometry. So, for example, in spin forms, you find that your geometric degrees of freedom are based on spins and intertwiners. In some other theories, it's based on some other things like lengths. So you can tell the difference between different quantum gravities from these path integral approaches. And because of that, you can actually ask fundamental questions like, for example, what are the fundamental degrees of freedom for quantum gravity? You can try to address kind of these questions. And here, I try to address just one of them in this topic. So the theme of this whole presentation is about causality violations. So also, we are focused on Lorentzian path integral. So in the computation of Lorentzian path integral, the main challenge you have to deal with is first how to compute the path integral. And it's a challenge because you have to deal with convergences and also high acceleratory integrals. And like we've heard in this talk, Bianca mentioned this yesterday, Euclidean path integral approaches have been one way, but they have limited use in this aspect. And Picard-Lifshitz method seems to be one way to kind of attack these high oscillatory integrals. And another question one can ask is, what are the configurations one should sum over in this path integral? And here we try to answer the question of whether we should allow some Lorentz topological changes, which are not really Lorentzian spacetimes. So I will argue at the end of the talk that the Picard-Lifshitz methods can also inform us about these questions. Maybe to make it a bit more precise, in 2 dimensions, it's been studied by already Raphael and Lyoko. For the causality violations arises in a form of that your action assumes some imaginary terms. And there are mainly two families of topological changing configurations. There is the Yamuk one and also the Trouser one. The difference is that they come with different signs of the imaginary parts. So already there's a question which configurations are enhanced or suppressed because it depends on the sign of the imaginary parts, right? And Raphael and Lyoko already postulated that, okay, the trouser-like configurations are suppressed, and it was based on the sign. And also in 4D, we have done some work in effective spin forms, and we saw that actually if you enhance Yamuk configurations, these lead to very nonsensical results. So there's this question, which configuration should be enhanced, which configuration should be suppressed? And the question I want to ask is there general formalism for these? So this is the theme of the talk. So I will start with a brief introduction of Lorentzian, Reggie calculus, I'm going to do this with discrete gravity. And then I'll do the path integral in the second part of the talk. Okay, so let's just go with the first one. So if you don't know about discrete gravity, this is just a basic summary. So Reggie calculus is one formulation of discrete gravity. It's based on a discretization of the Einstein-Hilbert action. And the main features are that it's based on a simplicial triangulation of your manifold. So the main features you need to know or compute are basically these dihedral angles, deficit angles here, and they are somehow corresponds to the curvature as you want in the continuum. And these deficit angles are distributed on codimension 2 surfaces. And so Reggie initially formulated this in terms of length variables, but there are other possible variables you can do this. Okay, so that's a basic introduction of discrete gravity. And to talk about Lorentzian gravity, one has to, the main structures one have to deal with are Lorentzian angles as opposed to Euclidean angles. So I'll give you a flavor of what Lorentzian angles here. I mean, Euclidean angles, you think of them as angles between vectors. On a circle, you rotate a vector to another angle. Here, in Minkowski, you'll be on Minkowski space, so here is a 1 + 1 space-time. And now the angles are seen as boost. And you have to also, so here we have to specify angles between vectors even across different regions of the Minkowski space. And there's a summary of how to define these angles. So for example, they are defined in this way. And the point here I want to make here is that you see the way we define these angles kind of depends on some choices between, like there are some imaginary terms here, and this depends on the angle. If there's a light ray between the vectors, then it picks up some factor of imaginary. And these are the imaginary terms that later show up in the action. So here, you know, depending on the choice, there are two options. So I define them L+ and L- for the different choices, right? Okay, so you can lift this, so it looks like this was in 2 dimensions, but you can do this in higher dimensions. But I give you examples of 2 dimensions. So I call them hinge causalities, these imaginary terms that we saw. Also, I think Bianca already showed some pictures yesterday if you were around. So these are examples of some triangulations that appear in 2 dimensions. So here we call such a triangulation irregular because you see that the bulk vectors here, they're exactly 2 light cones. Otherwise, then the triangulation would be called an irregular triangulation. So for example, there are more than 2 light cones, so you can see this as the trouser configuration. You know, you go from the past and there are 2 futures you have to go. And also there is this Yamuk-like configuration. So in higher dimensions, there are more conditions one has to go through, like there is edge causality, vertex causality, and Renate and Jordan has already mentioned this. I mean, I think currently it's still an open question how to deal with these type of causalities. Okay, so with path integral in mind, we are going to be talking about path integral. So what we want to do here is to somehow define a complexified discrete gravity. And to do this, we'll consider a very simple kind of complexification, right? So here, I define this inner product term between 2 vectors, so A and B are just vectors in Rn. And so if I define it this way, so there's this exponential I-phi term, which you can think of as some weak rotation angle. Then, I mean, using this definition, you can think of it that in the Reggie picture, that I somehow complexify all my edge lengths in the same way. So there's just 1 degree of freedom, which characterizes this complexification, right? And so the main object that you will focus on is these complex angles. So I write it here. Maybe the details of this doesn't matter so much, but these angles, like in blue here, actually generalizes all the angles you can define in Reggie calculus. And already, as you see here, there are 2 ways I can somehow analytically continue these angles from either from 0. So yeah. So I should say that when phi equal to 0, you get Euclidean for sure. And if phi equal to pi or minus pi, there's Lorentzian with different signs. And so you see that the Euclidean angle and Lorentzian angle are already branch cuts of these kind of angles. So we can analytically continue these by following the procedure. And I just mentioned here that one can extend this by analytically continue this, and you find that you can continue this to angles from minus 2 pi to pi. And you see, like, there's an example here, and you see that it's actually 4 pi periodic. Okay, so this somehow gives us a nice way to then define what the complex rejection is, because you can use these angles to then define what the deficit angles are, and you actually find that the deficit angles are defined in this way, and then you can use that to define the rejection. And the end result is that it's all well defined. So, so this is like the complex phi plane. Here you see, so if phi equal to 0, I pick up this imaginary, the Euclidean action, and phi equal to pi, I have these Lorentzian actions. But you see already the plus and minus signs show up here. So on this imaginary axis, there's already, what you find is there are branch cuts if my configurations are irregular, which means the light cone structures doesn't match. So that's why you see, so every time there's a branch cut, it will be on this line. But for regular configurations, these two terms are equal, so there's no ambiguity in defining what the Lorentzian Regge calculus is. So this is all nice. So yeah, so now I have this out of the way. I'll try to use this to describe how to do the path integrals in this aspect, and also how the causality violations show up and how to treat them. Okay, so I'll do this via the Picard-Lifshitz method, as I mentioned at the beginning. Okay, so the idea of the Picard-Lifshitz is it's simple, and it's also very practical, actually. The idea is that, you have this path integral you want to compute. It's very highly oscillatory. That's what it makes it difficult. So the idea is that you want to somehow convert this highly oscillatory integrals into some sum of integrals which exponentially decays faster. So this is the idea. And there is a very formal steps that one can follow to define all these things. So I just summarized them here. So the first step is that, you complexify your domain of integration. So here I just call it X complex. And then you look for critical points of your exponent. Here it will be the action here. So these critical points will be in the complex domain. And then you use the critical points in the complex domain to find the Lifshitz-Thimbals, which are the contours along which the integrand is decreasing, monotonically decreasing, and the imaginary part is constant. And then the last step is that then you want to express the original integration cycle into these Thimbals. So it's very clear how to do these things. And so we're going to apply this to deal with the causality violations that I mentioned before. And to do that, I'm going to use two very simple examples which also show up in quantum cosmology. So the first example is the no boundary proposal, which has showed up. You don't need to know any details of this for the purpose of this talk. The only thing you need to know is that in these cosmological spacetimes, the geometry of like the no boundary proposal look something like this. You have some Euclidean ball here, and then a Lorentzian de Sitter spacetime. And you can actually discretize this using these kind of triangulations. I will call them the ball model because they look like a ball. Okay, that's all you need to know. And the other example I will talk about is this de Sitter cosmology. So the idea is that there is okay, so I start from an initial cosmology for some scale factor I, and then I go to another scale factor final, and then so this, the one I call SH here, you can think of them as the lapse function. Okay, and so maybe one few little you need to know is that for this kind of models, there are some Euclidean saddle points, and there is a Lorentzian saddle point. And these type of models, I call them the shell model. Why? Because in the discretization, they look like shells. So there's a ball model and a shell model. And okay, So, about the causality violations. These two examples actually manifest causality violations. So I show here, like on these, so this is the lapse axis. So if for some values for the height or the lapse, you see that your configurations are only Euclidean. So this is on this side, if the height is 0 and higher, you only admit Euclidean configurations. But on this side, there's a Lorentzian configuration, but in some region, you have some causality violations. So this is where it's irregular. So I denote this by some shaded. And there's a regular sector. Okay, so already in these examples, we see this interesting phenomena already showing. And so the question is, how do these irregular configurations, does it affect the computation of the path integral or not? Okay, so so in the first example, in the ball model, so yeah, I still have here the complex plane. And it turns out that you can compute the Lefschetz-Timbo, and the Lefschetz-Timbo is this green line. It lies on the phi equal to 2 pi axis, which means that it picks up this Euclidean action here. And I have blue here. We call them the Antithimbals, which they act opposite like the Timbals. So there you have path. The paths are steep, ascending steeply. So right. So yeah. So actually, maybe this is a side result that you see that along these Timbals. So this is where you would actually deform your contour to. And we see that, yeah, this is along the phi equal to 2 pi, which actually leads to this choice of the action, the Euclidean action, which has been debated a lot in the literature, but it gives the same choice as Vilenkin and also Neil Turok and Job, who give a talk at the last end. So we actually confirm that maybe this is the correct choice to do. And the shell model is rather even more interesting. You have these interesting Timbals. So the green here is so this one is the Timbal. Yeah, so I mean, there are two saddle points, but let's focus on this one. I mean, this is not the actual Timbal. And there's a reason, because the anti-Timbal doesn't cross the original integration contour, so you only pick out this one. So maybe I did not explain before, but yeah, that's okay. But in this Timbal, you see that it goes across to this region and switches back to this region. And so in the computation of the path integral, we will have to deform the contour accordingly. So for example, in the ball model, if I want to deform this, so the original integration is along the Lorentzian axis, which is on this line. And there is a small irregular part here, which we saw before. So this is where the causality violations are. And you can try to compute the integral along this by deforming to this contour. And if you deform, so I show this in pink line, if you deform, so this is the deformed contour. So I'll do the integration here, and using Cauchy-Riemann, I can compute the integral along this direction using this. It turns out that this integration vanishes, so you basically have to do this integral, and it's easy. So the good thing is that you can also include the irregular regions, or you can try to find out without the irregular regions. But the point of this computation is that because you deform this part, it already picks up which side of the branch cut you should do your computation. And this picks out the side that suppresses these irregular configurations, or the causality violation configurations. So yes, so that's the main point. And also in the shell model, yes, so there is this original integration line, there are irregular configurations, but here you have to deform the contour along this path integral, and then you find that, so if I follow, so this integration will also vanish. Basically, I have to integrate along this line, but you see here, there's an irregular region, so this is more interesting, but you have to, because there is a branch cut, you have to somehow follow the, analytically continue through the branch cut, and somehow picks you here. But the main point is that here, if we had to choose which branch, it would have been difficult, but the Picard-Lefschetz already gives us a way to do this. So if I follow the Thimbals, I see that, oh, for small values of the labs, which is, so, I mean, the way you should read these graphs are, so this is the phi angle at 0, the length gives you the radius, which is the labs here. So, so yeah, when the labs is small, I somehow have to deform in this region, and then for large, I have to switch to this side of the branch cut. So I am somehow on different sides of the branch cut. But the good result is that also it always picks the suppressing side of the branch cuts for the irregular configurations, depending on the results. So that's the main message I wanted to tell you, which is that if you follow the Picalicious procedure, it always picks you to the side where these irregular configurations are somehow suppressed. And so the main point is that you can therefore include these kind of configurations in the path integral, and if you follow this method, it will not cause any problem. Okay, so that's the main message I wanted to tell you. So I'll just therefore conclude. So in doing this example, we've made a bit of progress computing the Lorentzian path integrals, and we saw that they are causality violating configurations, and they appear, they show up as branch cuts in your complex Reggie action. So this is in the discrete. And so, you know, using the Picalicious somehow gives you a way to overcome these conformer factor problems, which I did not mention, but they show up if you do the Euclidean path integrals, right? So first of all, the Picalicious gives us a good way. It gives fast convergence. And also, the point is that if you follow the Picalicious method, it allows you to include all the causality violating configurations, and you are fine. Okay. So as an outlook, so there are more examples one can test. So this was a very simple example. You can do this for higher dimensional integrals. Here we had only the labs function to integrate, but if the integration becomes complicated, it might, you know, be more challenging. But in principle, one can test these things. And also, I mentioned here application to effective spinforms. I think there's a paper on the archive this year, which you can check out. It somehow tries to answer these kind of questions. And I mean, one last point I made here is, for those who know about spinforms, there's the APRL spinform, that's the most famous one. Somehow these causality violations should show up because the kind of triangulations they consider are very much they very much show the causality violations, but there is no result if they show up or not. So with that, thank you.
Okay, so thank you, Seth. We have some minutes for questions.
I just have two comments. I mean, this method of using this Lorentzian Thimbals, I mean, it's okay. It's
Okay.
a valid method, but there is a simpler method which I used in my work, maybe from 10 years ago. Okay. You simply put a measure instead of complexifying your
integration.
You just put the measure. It's like you know, taking the real part of the complexified action to be a sort of a measure. But
okay.
And then by choosing a measure appropriately, you can make for example, the action to be finite, the path integral to be finite. So in that sense, there is a simpler method for regular for getting the.
Okay, I see.
And the second comment, the thing that you were considering that essentially you are calculating the Hartle-Hawking, I mean Lorentzian Hartle-Hawking wave function.
Right.
And but I think you should have chosen not the 4 simplex, but the 5 simplex, because it's a 4 simplex is like in 2 dimensions you're just choosing a triangle instead of choosing a tetrahedron with a cut.
Right. Okay.
Do you understand? You know, you are 1 dimension lower than what would be natural geometric.
No, it's a 5 simplex actually. Okay, I was gonna. So
you see, this is a 5. This
it's
is a 4 simplex.
Oh, 4, you mean 5 in 6? 5 simplex is a 6 dimension.
No, you take 6 of those. We use something which is like a 5. It's basically
But I see what you mean. Actually,
it's a 5 simplex in 4 dimensions.
Yes,
so
but
we use
it already. We use actually 600 cell.
yes, so it's
what?
We use it already. Actually, we use even a 600 cell.
yeah, I understand. But what maybe you should think of it as it's like a yes one. But this is just part of the simplex. Sorry, maybe it's a so you consider a 5 simplex. You put a vertex in the middle, and then you connect. So
yeah, you take 5 vertices and 6 vertices.
yes, right. So that's what we do.
One would be the 5 simplex, would be the
Yes,
boundary.
that's what we do exactly.
You did
This
that.
is what, and also we even do some more, which is you consider. So there are 3 types of homogeneous or irregular configurations one can do. So there's the 5 cell, which looks like the 5 simplex, and this is what we consider first. And there's a 16 cell, and there's a 600 cell, and you can do all these things. So you can do this and
no,
sorry.
For me, the simplest one would be this with 6 vertices.
Yes, we did that too. So
Sorry,
that's fine.
I think we can display something. Sure. We have a discussion session after. Can we have a last question?
Okay.
Thank you, Seth. Really nice description of all of this. You explained really clearly the fact that these causality violating sectors are suppressed. Have you thought about a regime of the theory in which, okay, they're suppressed, but they're still there, so that we could answer the question of as to whether, you know, causality violating region could contribute to our amplitudes?
I mean, in principle, they are there in the sense that you
I understand you to be saying they're exponentially suppressed.
Right.
Is that right?
Yes.
Yeah. I'm wondering if there's some regime that we could look for them where that exponential suppression is as small as possible. I mean, sort of trying to look for them empirically.
I think that's, I don't know, maybe if one can.
Maybe you can think of it like
yes,
during
sure.
the next talks and
okay.
then the discussion. Maybe you have an
yeah,
answer.
maybe let me think about this. Yeah. Thank you.
Okay, so thank you again, Seth.